Welcome back to multivariate calculus. In this video, we're going to be talking about simple regions and closed curves, or perhaps in the other order. But the ideas here, looking at the geometry, are going to give us a couple of tools to simplify further our discussion of path integrals, especially when a conservative force is involved. So without further ado, let me get my head out of the way and let's dive into this. Right. I could define these ideas algebraically. It's something that is certainly possible and in places useful. But for our purposes, understanding the geometry is good enough and quite a bit simpler. So a curve is called simple if and only if it does not cross itself. And a curve is called closed if and only if its starting and ending points meet. So in general, we can classify a curve as being simple or not, and as being closed or not. Let's move that down to give myself a little bit more space to draw these. Most curves are neither simple nor closed. There is a curve that is neither simple nor closed. Its starting point and its ending point are distinct from each other, and it crosses itself. A simple closed curve looks something like that. You can't even see where the starting and ending point are unless I point them out to you. But of course, you can also be simple and not closed, and you can be closed and not simple. When you have a curve that is simple, it makes doing calculus easier. When you have a curve that is closed, you get some really powerful results when you start to think about trying to do path integrals. All right. So there are times when it is very much worthwhile to emphasize that we are performing an integral on a closed curve. In order to do that, we put a circle on the integral sign. F dot dr, closed integral here, the closed integral of f dr over the curve C. The most obvious reason that having a closed curve is so valuable, if it turns out that our function f is the gradient of some potential function, we have a conservative force field, then the integral of f dot dr is going to be phi of our starting point minus phi of our ending point. I said those backwards, but ending point minus starting point. But on a closed curve, your starting point and your ending point are the same thing. So you get 0. All right, so recognizing that you have a conservative force and you have a closed curve, you know that the integral is 0 without doing anything else. That's one key reason for mentioning that you have a closed curve that you're working with. I guess then we're really going to be looking at situations where we don't have a conservative force field or a conservative vector field and hoping that we can get things to still work out in some way favorable. Right. For regions, we're going to get a little bit more technical, but the pictures, I think, speak for themselves. A region is called connected if and only if there is a path entirely inside the region between any 2 points. So a region that looks like that is connected. No matter where you draw your points, you can draw a line between them completely inside the region. Compare that to this region. To draw a line between these 2 points, you have to leave the region. Now, that's not to say that because you can leave the region is a problem, right? Consider this one where the most obvious path leaves the region, but there is a longer path that stays within the region. So that's still a connected region. Once again, visually, these make a lot of sense, and worrying about the definition can be more cumbersome than helpful. A simply connected region is a region that has no holes. The technical definition is there are no closed curves which contain points outside the region. Right. So there's your technical definition. Again, I'm not sure that the technical definition is all that helpful. Um, but here's a picture of a region that is not simple. To see our definition, if I draw this closed curve, notice that within that curve is this point, which is outside of the region, which I should probably draw in red to keep up my. So this is a region that is not simply connected. All right, it's in the name, but it's worth stressing that if a region is not connected at all, then it is definitely not simply connected. Simply connected regions are fairly straightforward. It's a region that encompasses the entire region. You didn't split it in two, you didn't punch any holes out of it. Think about the picture, don't get bogged down in the definitions, which is the opposite of what I usually say in my classes. But I think it's for the best here. Last thing, the boundary of a simply connected region is a simple closed curve. Or, in other words, if you have a simple closed curve, then the region inside is a simply connected region. All right, so we call the region R, and to denote the boundary of the region, we actually use the partial derivative symbol. And so from context, you have to pay attention. Is this symbol talking about a partial derivative, or is it talking about a boundary? Right. So it's the same symbol, has a completely different meaning when you're talking about a geometric approach, or actually a topological approach, but close enough to geometry for our purposes. All right, so it's the boundary of R, not the partial derivative or anything weird like that. All right. That takes us to Green's theorem. Green's theorem is technical because the technical details matter. Very often when I've stated theorems, I've said that there are issues with whether or not a function is differentiable that you don't have to worry about because in practical applications, you never come across that. Green's theorem, that's no longer the case. There are a lot of situations where this doesn't apply. All right, like I said, very technical. Let's consider R, a simply connected region. Let's consider the boundary of this, which is piecewise smooth. Piecewise smooth we haven't talked about. We've talked about smooth curves in general. A curve is smooth if it's differentiable and the derivatives are never zero. Piecewise smooth means that there are some number of points where that doesn't happen, but for most of the curve it does. Technically, it's any finite number of places where it is no longer smooth still gives you infinitely many places where it is, and that's good enough for us. All right, so smooth And simple and closed, that's given to us automatically because we have a simply connected region. Assume that my curve on the boundary is oriented counterclockwise. That's not that big of a deal, but it is something worth mentioning. If we change the orientation of our path, we are going to end up going in the other direction, and we'll get a negative sign. So counterclockwise follows the right-hand rule. That's the way we usually think about things. Finally, we need a vector field. We're talking about 2 dimensions, so we have little f of x and y, little g of x and y, and we want those to both have continuous partial derivatives. That's the one that's probably not going to be an issue. If this thing didn't have continuous partial derivatives, then we wouldn't have a thing that we're looking at. The things that are issues, we need to make sure we have a simply connected region. We need to make sure we have a piecewise smooth, simple closed curve that forms the boundary. And we have to make sure that orienting it counterclockwise makes sense. But if we have all of those things, then we can change the line integral, f dot dr, into an area integral, taking the partial derivative of the y component with respect to x, the partial derivative of the x component with respect to y, subtracting them, and integrating with respect to the area. And I claim that we're going to get the same thing. All right, so this is a tool which is more general than the fundamental theorem of line integrals, also harder to use, but it lets us talk about what's happening in a region by what's happening on its boundary, talk about what's happening on a boundary by talking about what's happening in the region. Right. I will mention that the applications and examples of Green's theorem are a lot easier to understand when we extend from 2 dimensions into 3 dimensions, although the equations themselves are going to be a lot uglier. But the key example here tends to be looking at work. All right. Calculate the work done by the force field f of x and y is equal to y plus sine of x e to the y minus x along the curve x squared plus y squared equals 4, counterclockwise, starting and ending at 2, 0. All right. So first thing, we're talking about work. That means we're going to be talking about a line integral. Remember, work is the integral f dot dr. Second thing I notice here is that the curve in question is a perfect circle, and we have the same starting and ending point. So we're looking at a closed curve. If this force field is conservative, then this is really easy. For a conservative force field, integral over a closed curve is always 0. But I'm looking at this, I'm getting sine, I'm getting exponentials. I don't see an obvious way of matching all that up. So I feel pretty confident without doing any calculations that this field is not going to be conservative. And so I could set up a path, plug things in, and start going. It wouldn't be much fun, but it would be something I can do. Or I can try to use Green's theorem. Take the partial derivative of the y component with respect to x, and you get -1. Take the partial derivative of the x component with respect to y, and you get 1. All of the complication is in path. The complication of the x component is with respect to x. The complication of the y component is with respect to y. So when you take the derivatives opposite, very good things happen. All right, so now we have that using Green's theorem, we can rewrite work as the area integral of partial g with respect to x minus partial f with respect to y dA. This is a circular region, so I could go the polar coordinates route, but look at this, even more convenient. The integral of the area of a region over the entire region is the area of the region. We can actually do this integral without doing any calculus whatsoever. Isn't that lovely? We have a circle with radius 2. The area of a circle with radius 2 is, well, in general, pi r squared. 2 squared is 4, so we get 4 pi. So the work done on this particle as it goes around this circle is -8 pi. And that's it. That's all we had to do. We're done. We can move on. Oh, too far back. Think about trying to actually work out that line integral using the process we've talked about before. Think about how much easier this is and breathe a sigh of relief. Let's take a look at one last example to show you that Green's theorem can actually be used in the other direction as well. I'd like to derive the formula for the area of an ellipse. Remember, basic idea of an ellipse. We'll deal with an ellipse centered at the origin. And let's try drawing that a little bit more nicely. That's a little bit more nicely. Ellipse has extents on x from a to -a, from b to -b on y, and the formula for an ellipse is x squared over a squared plus y squared over b squared equals 1. You can rearrange this to get that y is plus or minus b times the square root of 1 minus x squared over a squared. And so to calculate the area of any region is the integral over the entire region of dA. That's the definition of dA. And so I guess in this case, we can set it up as an iterated integral. X goes from -a to a, y goes from -b square root of 1 minus x squared over a squared to +b square root of 1 minus x squared over a squared dy dx. Please no. Let's not do that. Let's find something that's a little bit more mm, not tear your hair out inducing. So notice that we have integral here of just dA. And I can get, if I'm using Green's theorem on a vector field where partial g partial x minus partial f partial y is equal to 1, I know that this is what I end up with. I guess I also have to know what the boundary is. But for an ellipse, that's actually fairly straightforward. We've come across this formula before. We get a times the cosine of t, b times the sine of t. Right, that takes the unit circle, which is just cosine sine, stretches in the x direction by a, stretches in the y direction by b. T goes from 0 to 2 pi. All right, so if we can find any function that satisfies this partial g partial x minus partial f partial y equals 1, then we will be happy and we'll be able to use Green's theorem. There's no one option here. There's infinitely many choices, but I suspect that some symmetry will be nice. So if I set partial g partial x equal to 1/2 and partial f partial y equal to -1/2, that is one choice that will work. And I suspect it's going to be a choice that's going to make things convenient because I've got the symmetry there. Once again, there are infinitely many functions where if I take the partial derivative with respect to x, I get 1/2. But the simplest of them is 1/2 x. Likewise, there are infinitely many functions where if I take the partial with respect to y, I get -1/2, but the simplest of them is -1/2 y. So let's go with those. That means that my vector field f is -1/2 y, 1/2 x. My r of t is a cosine t, b sine of t. I've got 0 less than or equal to t less than or equal to 2 pi. And my area has now become the closed path integral of f dot dr. All right, so my x component, -1/2 y dx. My y component, 1/2 x dy. And of course, from my path, I know that x is a times the cosine t, which means that dx is going to be -a sine t dt. I know that y is b sine t, so I know that dy is going to be b cosine t dt. And making that substitution, my integral is going to become the integral t goes from 0 to 2 pi of, well, we have a 1/2. Y is b sine t. Dx is -a sine t. The negative will cancel out the negative that's already there. And then likewise, we have a 1/2. We'll have the integral 0 to 2 pi. X is a cosine t. Dy is b cosine t dt. And after having spent all that effort of separating all of this, Notice that if we factor out that AB, we can actually combine these things together into a single integral. And get sine squared t plus cosine squared t dt, and our favorite identity, sine squared plus cosine squared is 1. So we have 1/2 AB, the integral from 0 to 2 pi of dt. All right, that's going to give me t, evaluated at 2 pi gives me 2 pi, evaluated at 0 gives me 0. And all told, I get that the area of an ellipse is pi times a times b. And yes, that's actually the easiest way of dealing with that. All right, so we can use Green's theorem to take a path integral, turn it into a line integral. We can use, or take a line integral, turn it into an area integral, take an area integral, turn it into a line integral. Both of those are possibilities. I think that going from a line integral to an area integral is a little bit more straightforward. Helps if I start writing the correct thing. So I'd like you to calculate the work done by the force field f of x and y, has components y plus 4 cosine x minus 5 sine y, on the rectangular path that goes through the points 3, 2, negative 3, 2, negative 3, negative 2, and 3, negative 2. And you can see oriented in a counterclockwise direction. All right, take a couple of minutes, see what you can do with that problem, and I'll see you in the next video.